Welcome back to the third episode, where we are taking a hands-on look at how electric motors work. So in this video, we will focus in on magnetism, with some discussion and experiments that will hopefully give us a better understanding of the topic. As for myself, undoubtedly, like many of you, I have learned about the topic in school, but I've also forgotten a lot, and I don't feel all that confident in my knowledge base. I'm hoping that doing a hands-on look at the topic will make a bit more of an indelible impression on my brain. Of course, I'm using research as need be to avoid giving out blatantly incorrect information, but at this stage, I still want to stay away from heady formulas and try to maintain a grounded feel to the discussion, the best I can at least anyway. Now, as you've likely already deduced, I'm not a scientist or a teacher, and this is not intended as a scientific lesson, so just keep that in mind when watching this video. So first off, let's touch on the basic things that I do remember about magnetism, things that I suspect most people probably have some idea about. So magnets are attracted to and can stick to things made of iron, right? Magnets emit a magnetic field, as can be seen with a simple iron filings experiment. Some fields loop back, some seemingly go out to infinity. Fields of the magnets have a north and a south pole. Pushing the same poles of magnets together cause the magnets want to push apart, whereas opposite poles attract and ultimately want to stick together. So the Earth acts as one huge magnet, right? With a field going around between the north and south poles. Compasses make use of the Earth's magnetic field to point to north. Electric magnets can be made by winding an insulated wire around an iron core and running a current through it. The size of the magnetic field will be relative to the number of wire windings and the amount of current being used. Direction of the current, or the direction of the windings, decides which pole is either the north or the south pole. And I think that's pretty much it for me. Probably a pretty typical level of knowledge, I suspect, for an engineer who's not working specifically in the field of magnetism. So let's get going with expanding our understanding a little bit further. First, let me share what I learned after a little bit of internet research. Now, there are actually 5 different known types of magnetism that materials can have, but we're going to stick to just looking at good old ferromagnetism, and also take a look at electromagnetism. Examples of ferromagnetic materials include iron, cobalt, nickel, neodymium, and others as well. I think I read somewhere that the atoms in ferromagnetic materials create a magnetic field because their electrons spin in the same direction. Whereas for non-magnetic materials, the spins are such that it cancels out any magnetic field. In any case, the orientation of the electron spin is what decides the orientation of the magnetic field in the ferromagnetic materials. If we just look at a piece of ferromagnetic material in a natural, say, non-magnetized state, the electron spins of the atoms within are orientated chaotically, right? And the combination of the random mix of orientations results in no effective magnetic field being generated. It's only when enough atoms have similar electron spin orientations could the combined fields generate an effective magnetic field. But not all ferromagnetic materials are the same. Some have the ability to stubbornly lock in the orientation of the electron spins, while others are loosely held with the orientation easily affected by external magnetic fields. It's a little bit like a wind vane moving around in the breeze, right? Well, that's the way I sort of think about it. Technically, the stubborn ones are known as hard magnetic materials, and the loose ones are soft magnetic materials. Naturally, permanent magnets are made from hard magnetic materials to ensure they keep a magnetic field indefinitely. But to make a permanent magnet, during manufacturing the electron spin's orientations must be aligned. First, using heating, powderization, or other methods, the material's internal atomic structure is temporarily loosened up, then a strong magnetic field is applied to commonly orientate all those electron spins. Finally, depending on the manufacturing method of course, a combination of molding, compaction, or cooling techniques are used to set the permanent magnet. Now, just as heat is used when making permanent magnets, it can also be used to destroy them. I think you've probably heard of that. If you apply too much heat to a permanent magnet, the atomic structure is loosened up again and the common electron spin orientation lost, along with the magnetic field of course. Now, the most common soft magnetic material we know about is iron of course, and of course we know that iron is not a permanent magnet. But by bringing iron into the influence of a magnetic field, electron spins will orientate with the influencing field, which in turn results in the iron creating its own magnetic field. Now, a little side note here, some soft magnets can actually retain some of the magnetic field after the permanent magnet is removed, but typically this is pretty weak and it's not a permanent magnet of course. I think a key thing to remember is that permanent magnets are not simply attracted to iron, even though it sort of seems that way. A permanent magnet actually induces a co-orientated magnetic field into the iron, which in turn causes the attraction force between the fields, and not the materials as such, of course. You also need to keep in mind that an inducing field will only affect the atoms in the iron that it meaningfully interacts with, which can result in localized or partial magnetization. Of course, a field that's too far away or too weak is not going to swing it, literally. And then there are also cascade effects to be considered. I mean, once the iron starts to create a magnetic field, if strong enough, this field will then have the ability to orientate other iron atoms as well, right? Be it atoms in the same object or another soft magnetic object nearby. Now, one very interesting thing about soft magnetic materials is that they can behave a little like magnetic field amplifiers, right? This is because you can use a smaller magnetic field to in turn induce a much larger magnetic field. But as with any ferromagnetic material, soft magnets have a physical limit as to the size of the magnetic field it can actually generate. Once all the atoms' electrons are all orientated in the same direction, you reach the maximum potential, or reach what is called the saturation point. Now, saturation is probably a useful term to keep in mind, as it is often used to describe when maximum potential or capacity has been reached in an electrical system or device. Anyway, with this understanding, it is obvious that the more atoms or mass you have in a ferromagnetic object, the larger the magnetic field you can actually generate. And another factor that affects the maximum possible field size is what material you're actually using. I think most people know and have likely experienced how powerful a small neodymium magnet is compared to say a fridge magnet. So clearly different materials have a potential to create a larger magnetic field than others. But what about changing the shape of the object? Well, actually this will not increase the overall magnetic field potential, but using, say, pointier shapes for the poles can focus and create stronger fields in localized areas. So let's try to neatly sum this up a bit. Material type and mass defines the maximum field potential. And to what degree the electrons spin in the same orientation decides how much of that potential is actually being applied. Shape itself can only be used to focus the field strength, but it doesn't affect the overall potential. And finally, one little tidbit on materials. Here are two nuts. They look much the same, right? But this one is plain old steel, and it's magnetic, and the other one is 304 stainless steel, and it's not. So what's going on here? Both made of iron, right? Actually, mild steel is apparently around about 99% iron, and this 304 stainless steel should contain around about 70% iron. So there should be enough iron in there for it to be classed a ferromagnetic material, right? But clearly the material mix and manufacturing process results in what is effectively a hard magnetic material. It seems to me it behaves just like a permanent magnet that has been made without applying the magnetic field during the manufacturing process. So the atom's electrons have not been orientated and instead have been locked into a permanent state of no magnetic field. Alright, enough of the blah blah blah, as Greta would say. Let's get on to some more practical stuff. All of the experiments we'll be doing will be based on these whiteboard magnets that I had on hand. They are 19mm in diameter and 9mm thick. Now, I'm not really sure what these magnets are made of. They seem pretty powerful, but clearly they're not neodymium magnets. They're sort of a dark color underneath this paint and are easy enough to separate. In an effort to try to have a somewhat meaningful results of these tests, other objects I will use will be using the same sort of basic dimensions. So it's a comparison of things with common volumetric and shape, but the weight obviously is going to vary between the different types of things we're testing with. For these magnets, the poles are located on the faces here, and the field strength feels somewhat dome-shaped with the force peaking around about the center here. And with a little bit of skill, we can connect the magnet side by side like this, with the alternating north-south poles facing each other. Now, in doing this test, it sort of sprung to mind that the Earth and compass needle must be behaving in the same side-to-side magnetic situation, right? So in fact, if that's the case, the geographic North Pole must actually be the magnetic South Pole. And it is. I googled it, and it was. Well, I guess I probably should have known, but whatever. So as with these side-by-side magnets here I'm demonstrating, the alternating north and south poles of the Earth and the compass needles are attracting each other, right? And of course, naturally, the Earth's slightly larger inertia keeps it in place, while the compass needle, which is on that little pivot, spins around and lines up with the Earth's magnetic field. Okay, enough of that little diversion. Things are about to be getting serious. First, I machined up this little steel slug to be used in the testing with the magnets. Now, looking at the statistics, it seems a lot of people seem to enjoy watching me make a terrible mess of machining things, so I've included this little sequence for your pleasure. I did try to sharpen some of my old tools with a stone, possibly made them worse. Get it somewhat centered. Mark off where I want to part it. You can hear the low RPM is not that stable without any load. That's the auto compensation hunting a little bit. Now I was able to get a good way through with the parting tool. Still a lot of chatter, but the lathe seems to have plenty of power. Anyway, I finished the cut with my reciprocal saw, a lot quicker and a lot less noisier that way. And face it off. This tool I'm using really sucks. It chatters pretty bad. And I'm too lazy to change it at this point, so I'm just going to go with it as it is. But even with this rotten tool, you can see I'm getting some pretty decent depth of cuts. I'm pretty sure that with a better cutting tool, a 3mm depth of cut in mild steel should probably be no problem with this lathe. Total overkill using the angle compound for this little bevel here. And parting off the work here. Not terrible, not great. I'm using a file to add the other bevel here, because it would be quite difficult to rechuck and cut that bevel in later. And finish the puttying cut. Refit the work to the chuck. And skim off the face to make it look pretty. So here's the result. Not too bad overall. It weighs about 17 grams. I have 6 of these whiteboard magnets, and I'll quickly go through and weigh each of them to make sure that they are all the same. Yep, they're all the same at 9 grams. I will secure the piece of steel in the scale using a 3D printed stand here. testing the release strength of each face of each magnet to get an idea of how strong they are. This test method is probably a bit iffy, likely responsible for a reasonable degree of error, but we do get an average release power of around about 264 grams on either face, so I think it's probably good enough. Actually, surprisingly, these magnets are pretty strong, I reckon. The combined weight of the steel and magnet together is only 26 grams in total, right? But we see a peak release force of up to 290 grams. That's like a 10-to-1 ratio. Also interesting to note is the power is not necessarily symmetrically for the north and south faces of each magnet. So, these magnets are clearly not precision manufactured by any means. Now, when I first started thinking about doing the testing on the scale, I was sort of playing around doing the testing by hand, but those results were pretty useless actually. I mean, you couldn't really get anything that was, you could draw any logical conclusions from. So I designed this frame and screw mechanism to use with the scale. No dramas with 3D printing this one either. Did need to include a couple of little custom supports for the hooks where it hooks onto the scales. It was a bit of a long print all up. I think it took about 9 hours in total. But the result was pretty nice, and thankfully I got it right first go. I also printed out these feeler gauges, 1, 3, 7 and 15 millimeters in thickness. The frame sort of fits on like this, and the item to test goes in this space with the cap securing it like this. The screw holder cap also has 1 millimeter thickness in the cap, so this gives me a total of 1, 2, 4, 8 and 16 millimeter distances to test with, doubling the distance with each test. First, let's do a distance test with the steel fixed on the scale and the magnet in the frame. At 1 millimeter distance, we're seeing a pretty large amount of force of around about 174 grams. And this is compared to, say, the average of 262 grams that we saw for the release test, right? But this force drops off rapidly, and clearly in a non-linear fashion, with only 1 gram detectable at a distance of 16 millimeters. So what we are seeing here is the effect of the steel's induced magnetic field becoming less and less as it moves further away from the permanent magnet's magnetic field. But this should be different to what we would see when two permanent magnets interact, where the field strength of each would remain exactly the same even as the distance increases. So let's do that experiment next. First we will do a test with a permanent magnet mounted in the scale and the frame with both the north faces facing each other, so the magnets try to repel each other. Well, at 1 millimeter we are seeing 302 grams of force. Pretty powerful, and much more so than the 174 grams we saw with the steel. The fall off is still pretty quick and non-linear, but the rate that the fall off occurs is much slower than that we saw with the steel. Even at 16 millimeters, we're still seeing a noticeable force of 26 grams. This is still 31% of the force of what we saw at half the distance. Now compare that with the drop-off rate we saw with the steel slug, where it only retained 10% of the 8 millimeters force when the distance doubled to 16 millimeters. I think this really gives us a better sense of how the magnetic fields interact and induce the magnetic fields in those soft magnetic materials. And just to maintain our sanity, I will swap the direction of the magnet in the frame so that it has the south face being attracted to the north face of the magnet mounted on the scale. And there you have it. I think we can see that the amount of force at each distance location is basically the same, regardless of if the magnets are either repelling or attracting each other. Next, let's move on to testing electric magnets. If you missed the last episode, then don't forget to check it out and see how I made these nice little coils. The coil on the left has 211 winds and can be used as either an air or steel core. The coil on the right has 324 winds and it's only an air core. As we did with the permanent magnets, first we were going to do some release tests with the steel piece mounted into the scale, where you can see straight away that the steel core 211 wind one gives far more power with 37 grams per amp compared to the 2 or 3 grams per amp for the air core ones. And clearly it goes a long way to prove the point that a relatively small magnetic field can induce a much larger magnetic field into a soft magnetic material. The test also seemed to prove that the coil that had more windings could actually give more force for the amount of current being put in. But as both of the air core coils were really only giving a couple of grams measured force, it's pretty hard to draw a solid conclusion at this point. So now let's stick a permanent magnet in the base with the north face facing out and do some distance testing with the 211 wind steel core electromagnet. We'll run the current in both directions to measure the attraction and repelling forces, and we'll also measure the force when the electromagnet is switched off. Well, that result is not what I had in mind, but let's think about it for a minute. At 16 millimeters, we are seeing a symmetric push and pull force of about 4 grams. At 4 millimeters, we are still seeing some positive push forces, but below that, we always get a net attraction force, regardless of if we reverse the current or even switch the electromagnet off. So the answer lies in the measurement for the off state, I believe. Even though the electromagnet is unpowered, we can see that below 8 millimeters, attraction starts to happen. And that attraction gets pretty strong by about 1 millimeter. This pretty much tells us that the electromagnet's steel core is having a magnetic field induced by the permanent magnet itself. Even though this seems pretty obvious now, originally I was not contemplating this effect. But the simple fact is that an electromagnet with a steel core cannot behave exactly like a permanent magnet. Electromagnets' steel cores are still susceptible to being influenced by other external magnetic fields, and not simply by the field generated by the coil wrapped around it. If the coil is in the off state or another external magnetic field is much stronger than the one generated by the coil itself, then the external magnetic field will play a larger role in the ultimate magnetic field that is induced into the steel core. And this is what we're seeing in this experiment as we bring the electromagnet closer and closer to the permanent magnet. Let's do a quick experiment to understand this behavior a little bit better. I'll mount up this green magnet in the scale, north side up. Here is a much weaker fridge magnet. You can see pushing the like poles together always gives us a pushing force, even when we're very close. It peaks at around about 60 grams. If we use one of those green magnets, we get over about 300 grams. So you can clearly see this fridge magnet is a much weaker magnet. The force is so weak, it can barely hold the weight of this 17 gram steel slug. So we're going to tape it on here for the experiment. As you can see, the steel slug has now been induced to be magnetic by the weak magnet. Now let's do the same scale test again. This time as we approach, we initially see a pushing force and it's peaking out around about 5 grams. but then as we get really close, the force switches. It starts to be a pulling force of over 80 grams, and then I can't hold it any longer. What we're seeing with this permanent magnet test is the same thing we saw with the steel core electromagnet test. Initially, the weaker magnetic field is inducing the field into the steel just fine, but as the stronger field gets closer, it has more effect, ultimately overpowering the weaker magnetic field. So in those initial steel slug release tests using the steel cored electromagnet, we could clearly see the benefits of using the steel core compared to that of the air core. But this second test, this time using permanent magnets, shows us special consideration must be given to how permanent magnets will interact with the steel core of electromagnets. Strength of the permanent magnet, distances involved, shape and size of the steel core, magnetic field of the coil, these are all going to be important factors to getting the desired force interaction between the permanent magnet and the steel cored electromagnet. Okay, let's move on to doing the air core electromagnetic experiments and see what that gives us. First up is the 211 wind air core electromagnet. Now the overall strength is very weak, peaking out at 21 grams in this test, far weaker than the permanent magnet. But just as we saw with the permanent magnets, the push and pull forces are staying symmetrical. Also, the rate of fall off closely matches that of what we saw with the permanent magnet test. One notable thing about this test is that it ran much hotter than that of the steel core using the same amount of current. In fact, it was so hot that the resin material smoked and began to break down, and the PLA in the frame even started to melt a little bit. It reminded me of something I read somewhere. It said something about the benefit of steel cores giving better heat dissipating properties, and clearly that was the case in this experiment. Next we will do the same test again, but this time with the 324 wind air core electromagnet. I'm reducing the current a little bit to try to reduce the heat in the test jig and stop it from melting down. Well, there are not too many surprises here, much the same results as the last set of tests we did, with the rate of force decline nearly an identical match actually. The increased number of winds is clearly giving us more force per amps, but it's interesting to note that with the 324 wind, we're only seeing around about 85% of the milligrams per amp wind of that of the 211 winds coil. Now, I was expecting this to be much the same actually, but when you really think about it, the shape of the windings is different. So this is going to affect the shape of the field, and so likely the field strength per winding amps is actually the same, but the difference in that shape is likely the reason for the lower effective force that we're measuring here. So in this last set of experiments, we're going to test the performance and behavior of electromagnets when they're driven by PWM control, and compare that behavior to linear current type control. So first up, I need to design and make a PWM generator. I'm using an AT-Tiny 85 for the microcontroller. And I'm adding a little OLED display connected using I2C bus. 2 buttons directly connected, as only 2 ports remain available. Could have added more buttons using some resistors and messing around with the ADC, but it's not really necessary for this build. And then from PB4 port we will get the final PWM signal. Here I will also add the MOSFET to drive the load and include a protection die and a small cap to try to deal with any garbage caused by the electromagnet. Now let's get that on the breadboard. But don't expect any Ben Eater style breadboard beauty from me. You've got to love that tiny little microcontroller and display. All very cute, right? I'm going to stick the MOSFET stuff down here on the end. I've got the software already loaded and power it up from a USB breadboard power supply module. It always starts up in the off state. Okay, press both buttons together to toggle between run and stop states. First I'll add a little LED here for some basic testing. Adjust the maximum voltage and therefore the maximum brightness. I'll reduce the setting and the LED darkens. I'm going to have to get you to ignore that flicker. This is just the camera shutter and display refresh rates clashing. And back up to make it brighter. You can see the value is set between 0 and 255, but for ease of use I'm also showing the duty cycle as a percent, shown just below that. Off, then on. Yep, all working well. Let's take a look at that on the scope now. Here it's preset to 50% and I've got it stopped. Now turn it on and we can see the 16 kilohertz signal with a 50% duty cycle. Switching between 0 and 5 volts. Yeah, it's all looking good. Let's drop that to 25%. Yep, there it is. All working as one would expect. And then 75%. Yep, looking good. Switch it off. Switch it on. Ramp it up. Ramp it all the way down. And now to test the minimum setting. It gives about 0.75 duty cycle according to the scope. So for the electromagnetic testing, we will just use the same setup that we used in our last electromagnetic test with the permanent magnet in the base and the 325 wind air core electromagnet in the frame. First I want to get some baseline numbers, so we will run the PWM at 100%, meaning it's going to be fully switched on, no switching, and then adjust the current using the power using the linear controls of the power supply. First set the baseline at 0.8 amps, and this gives us a force of 18 grams. Now reduce this by 50% to 0.4 amps, and that gives us 9 grams of force, which is in fact 50% of 18 grams. Wind the PSU back up to 0.8 amps for our PWM testing. Set to 50%, and then set to run. We see 7 grams of force and 318 milliamps of current. So the PWM is clearly not giving us a linear result, but even so, the measured force and current relationship seems to be the same across the range. If we crank the PWM up to about 58%, then we get the 9 grams of force and 0.4 amps. So effectively we get 50% power when we set the system to 58%. At 37% PWM, we see 4 grams and 200 milliamps. So to get 25% effective output, we need to set it pretty high, right? And when we do actually set the PWM to 25%, we only see 2 grams and 100 milliamps. And finally, if we keep winding it down, we can get to 0 grams. And that comes in at around about 14% PWM. At 75% PWM, we see 12 grams and 570 milliamps. At 80%, 13 grams and 608 milliamps. At 90%, 15 grams and 700 milliamps. And finally, at the highest setting, just before fully on, 17 grams and 780 milliamps. So yeah, not really a linear result, but I'm not really all that surprised. There was always going to be somewhat of an overhead related to the time the MOSFET spends switching between the on and the off states. Naturally, this overhead is going to be more pronounced at the low end of the PWM scale, and that's pretty much what we're seeing. And I guess if need be, either mapping or an approximate logarithmic function could be applied in order to obtain a much more linear control in these types of situations. So taking a look across all the numbers, we are seeing a pretty consistent 70 milligram per amp winding across the range of the PWM settings. So it doesn't appear at all that the PWM is affecting the basic force behavior in the sense of how much amps we put in and how much force we get back out. And I think these results also further confirm that the amount of current being applied is having a pretty much linear effect on the forces being generated. So I think that's about it for these experiments. Clearly the most important thing I learned, or most likely relearned, is that permanent magnets and magnetic materials like iron all belong to the same basic family. At an atomic level, they create magnetic fields in exactly the same way, and really only behave differently because one is stubborn and the other one is freewheeling in how they hold their magnetic field. I also found out that while using a steel core for electromagnets can greatly increase the magnetic field strength, it can also increase complexities. You really need to consider how any other magnetic fields that could come into the proximity of the steel core could negatively affect your design's intention. And finally, and this is a big one, modern permanent magnets can be compact and impressively powerful things. No power required. By comparison, I did not get that warm fuzzy feeling with electromagnets. Well, other than the immense heat that they give off. Clearly my test setup is not great, and as with most things, changing the scale would likely change the efficiency. But even so, I was really pumping a reasonable amount of power into those electromagnets, only to achieve what is a tiny fraction of the force that we can achieve with the same size cheap permanent magnets. Ultimately, comparing electromagnets with permanent magnets seems a little like comparing apples to oranges, so expecting them to provide the exact same performance seems a little bit silly actually. I feel it would probably be better to understand these differences and focus on the strengths of each when using them in your designs. Now clearly I still have a lot to learn, but I think doing these experiments gave me a more intrinsic understanding of magnetics, and hopefully that will help me for future projects. And I do hope something in this video has also helped you too. The next video will probably be the last for this series for now. We will actually be playing with some homemade motors or something like that. Anyway, it should be interesting and hopefully fun, so I hope you do join me then. See you next time!